Um, so, were you able to complete watching the lectures? Yeah. Okay. Then I think Wednesday works better for the session instead of Monday. All right. So, week 5, 6. What had we done? So week 5, 6. We saw like we started with supervised and we saw the regression part, right? We saw regression. We saw rich regression, linear regression, master regression, and so on. Then from now onwards, like from week 7, we are starting with our classification problems, right? So classification, as we said, like if we have some classes in which if we want to put my data set into, for example, whether when we take the spam email spam problem, we saw that given an email, we have to check whether this email would go to the spam folder or will it go to the non-spam folder, right? So such kind of problems is under the classification, or maybe let's say if there is some kind of like we want to predict the sentiment. Sentiments are positive for the reviews or negative for the reviews. So again, it's more like you're putting in two classes, right? So such kind of problems comes under the classification. But now, in general, in this week, we are dealing with the binary classification problem. So, how does the binary classification problem looks like? So, binary classification, right? So, in binary classification, what we are seeing, the data set that we have, so D, let's denote as D. So, my D is x1 comma y1, x2 comma y2, so on to xn comma yn. Now again, here we don't have just xi's, we also have the yi's along with it, which are the labels. So here my xi's belongs to RD, which are teachers, and yi's belong to some classes. Since we're talking about binary classification, it is going to only have two classes. So it can give 0, 1. Okay, so my yi's belongs to only these two. Either it is in class 0 or it is in class 1. Right. So this is how my data set looks like. Now, when we were looking at the class regression problem, what were we looking at? So in case of regression, our goal was to come up with a model H which takes the input in RD and gives us a predict a real number, right? That was in regression. So we were interested in finding out in predicting the real valued the real numbers for our problem statement. Was it? Okay, Prashant, you have asked. No, so in class, it's not that it will only have a binary classification problem, but we are starting with the binary classification problem because whatever we see here, it's you're just going to, you can build it up for the multi-class classification problem as well. Okay. So it's not just, I mean, the real world problem are not just binary classification, it's mostly multi-class classification problem. But here we are going to look for the binary classification problem this week. So, okay. So this was our goal in regression. We wanted to find out a function h or this. What was this function h? This function h is a model. We want to learn this model which takes the input as features in which are in RD and it gives us a real number. But now, when we are looking at this classification problem, then what happens? Now we are no longer looking for predicting a real value. What we want is we want to just predict. So it takes input in RD and it gives us either 0 or 1 because my yi's belongs to 0, 1. So it will predict either 0 or 1. So this is our goal in binary classification problem. We want to find out what this H is, right? So that is a setup. Now again, when we go back to the regression, how does the average, I mean, what does the loss look like? So there the loss look like sum over, or maybe we can call ya hat minus ya whole square, right? I is varying from 1 to n, right? Where ya is the predicted value for my model. Now, this is a loss we were looking at in case of regression, and we wanted to minimize this loss, right? We wanted to minimize this loss. So to want to minimize this loss, now what do we know? We know that like whatever this model is, like let's say in case of linear regression, the model that we had defined was W transpose X, right? It's a linear model, and we, based on what the loss we get, so whatever the loss we have, we are interested in finding. We were interested in finding that W, which gives us the least loss, because that is what we would want. Like if we have some test data coming in, I would want that if I give this test data to my model, it should predict as lesser loss as possible, right? And that would be considered ideal. We would want the loss to be lesser. So we were interested in finding this loss, and we wanted to minimize this. But now, if we come back to the classification setup, so we know we want to learn this edge. Now, what is the loss in case of classification? First of all, it's a 0-1 loss, right? So in case of classification, uh, the way we define loss is okay, sum over I varying from 1 to n. Now, what do we want to check? Here it was squared error, right? But now here, what do we want to check? We want to check whether the h of xi that we have, the model that we have learned, which is h, if I give this model this input xi, then whether this value of h of xi turns out to be equal to yi, which was a true label, right? For example, let's say you have some xis with you, and these xis, I mean, you are learning this model based on the training data you have. So the training data will also have the labels with it along with the features, because it's a supervised learning problem, right? So you will also have, along with the features, the true label you will have. But now let's say you have some model that you learned, so h of x, and now this is your predicted value, right? This is your prediction. Now in this case, what do we want to check? We want to check whether this predicted value that I have, and again the prediction is going to be what? Either 0 or 1, right? So in case if my let's say if there are 5 data points, 1 2 3 4 5, ya let's say was 1, maybe this is 0 1 0 1, okay? And let's say the h of xi that we get is, let's say the prediction is for the first data point is 0, for the second data point it is 0, for the third data point it is 1, for the fourth data point it is 1, for the fifth data point is 0, right? So now what we're looking at is this indicator function h of xi is equal to yi, right? And what does this indicator function mean? Like what does this denote? Like if I'm saying h of xi is equal to yi, what does it mean? Anyone? If you know, what does it mean by indicator function?
It gives the boolean.
It gives the boolean, right? Exactly. So this will take, if in case your h of xi is equal to yi, this will take, this function will take the value as 1, and if it is not equal, if h of xi is not equal to yi, it will take the value as 0. Okay. So that's what this indicator function here means. So if I look at this example, what do you think this value should come out?
0011.
The number of ones means adding all the ones.
The number of ones?
Yeah.
No, tell me this value. What is this value going to be?
1.
Yeah, one.
Are you sure?
2 out of 5.
2.
No,
It is 2. This value is 2. Why is that?
How?
Yeah. So what does
Yeah,
x
yeah, 2 years from 0, 0 and 1, 1. Yeah.
h of
Yeah,
xi has to be equal to yi, right? But
yeah,
if you
two
look at
times
the
relation.
first example, h of xi is not.
Second and third is true. Second and third.
Yeah, second and third is true. So this will give you 1. This will give you 1. And sorry, it was 3 actually. Sorry. So what are the places where h of xi is equal to yi? So it is 2. Only for the second observation and the third observation, I am getting h of xi to be equal to yi. And remaining all the 3 observations, these 3 observations, I am getting h of xi to be not equal to yi. So those values will take it to be 0. So if I have to write the loss, and again it is actually defined as 1 by upon n summation. So since it is number of data points by 5, so 1 by 5, and I will write. So this is going to be first one is 0, second one is going to be 1, third one is going to be 1, fourth one is going to be 0, and fifth one is going to be 0. This is it right? Yeah, 2 by 5. Right. I think I earlier said 3, but yeah, 2 is correct. So 2 by 5 is the loss that you will get for this function. All right. So unlike the regression problem where we are trying to look at the squad loss and trying to find that the optimal weight from there because we wanted to minimize this loss. Here in this case of classification, we have the 0, 1 loss, and this is how we define the 0, 1 loss to be. Okay.
Ma'am, can I ask something?
Yes, tell me.
Ma'am, you said that this quantity, summation quantity is loss. What if all the values got matched? Means h of x equals to y of I. All values got matched. All values are true. Then we will get 5. Okay.
Sorry. Actually, okay.
Misclassified है.
Yeah.
This is actually not equal to. Sorry. Uh, I messed this in, not equal to. So the loss, the way we define, let me write it here. So the way we define the loss, it is 1 upon n sum over h of indicator of h of xi not equal to yi, right? Because we want to see where is it that it is not equal, like how many points we are misclassifying basically. So that is the loss. So now it is going to be
3 by 5.
3 by 5. Okay, this is wrong. Yes, Kiran.
Ma'am, when are we really using test data? I have this confusion from
When are we using what data?
test data. Like
Test
we are
data.
not using it, ma'am, but when we are coding now, we are using both test and training data. Like
No, when we are training, we are using only the training data. So you would have seen now in week 6 that you divide your data set in 3 parts, right? One is this one training data, one is validation, and one is test, right? So on the training data, you fit a model, right? So you will have, and it's more like 80-20, 70-30 is the ratio that we keep, right? So that is the ratio that we keep. Now, whatever training data we have, we fit our model, and on the model that you get, let's say I had a training data here, and based on that, I got H. Okay, so I will repeat the ratio. Hold on. So let's say I get the model to be H. Now, what do we do? So once we have this, but now we want to test this, right? So how this is something that you obtain from the training. This is not something that you obtain from the test or validation. So how will this H perform if you give some test data? If you on this model, if you feed your test data, how will this model perform? That is your goal. That is what we would want to check. and we would want the test error to be smaller, not the training error to be smaller. So test error is something that we are looking for. So now for this H, we want how will this perform on this test data. Okay, so let's say if this was my total data set and I have kept this for my testing, then I will use this, and before even going to go for testing, there is something called the validation data set, validation data, right? So cross, that is where we use the cross validation and all. So what we do is like you have seen the k-fold cross validation, one-fold cross validation, and so on, right? So you check on, you find the MSE in case of regression. You find those MSE and see which is this ideal value of whatever parameter that you have, that is giving you the least validation error, like on the validation data, which is giving the least MSE, right? And based on what you get from there, now I am going ahead and doing the testing on it, right? So now whatever W, let's say we get for the regression, now I can go ahead and see let's say W star. We will expect now this the model H, sorry, not W star. We'll expect now this model HR to be performing well on test data. So even in coding, when you are doing it, you would have done the split of test, training, and validation. Okay. Okay. So someone was asking, could you please repeat the ratio? So this ratio you're talking about?
Yes, ma'am. I asked her. Could you please?
So see, what is this indicator function telling you? This is saying it will take the value 1 if h of xi is not equal to yi, and it will take the value as 0 if it is equal to yi, right? So if they are equal, it means loss is 0, right? So that's how it is defined in this way. So now what can we say? So this will turn out to be 1 upon 5. H of xi is not equal to yi, which happens in the first case. Second case, it is equal, so it should be 0. So 1 plus 0 plus, for the third data point, it is again equal, which does not satisfy this condition of h of xi not equal to yi. So it is 0. Then for the other two, it is 1 plus 1. So you have a total of 3 misclassified points. You have 3 misclassified points. So the loss that I'm getting for this data set is 3 upon 5.
So, ma'am, what does 2 by 5 indicate?
No, that was wrong. So this is correctly classified point, which is not our loss. Our loss is plus 3 by 5. So this represents number of fraction of misclassified point, you can say. So what is 3 here? 3 is number of misclassified point, right? Right? This is what it is.
Okay, ma'am.
Okay. Okay, so Prashant, you have a question. We always use rich and lasso algorithm to fit a model or single model is able to fit a model. I'm asking if the both model is prevent overfitting happen in any model. Okay, so I think your doubt is for the regression, correct? Yes. So yeah, so overfitting, okay, so overfitting can happen in any model. That's true. So for the, like when we're using this rich and lasso, yes, it is like helping us in preventing the overfitting. But now when we are looking at the classification problem, we'll see um, like how to deal with such things over here once we move forward. So there are techniques, and we'll see it. Okay, so that was about the loss in case of a binary classification problem. Okay, so what we are saying is, like, whenever there is a mistake which my model makes, I am penalizing it by 1. Otherwise it is zero. The loss is 0. So in general, like this was for this example that we were looking for. So in general, the loss of a model is basically 1 upon n indicated of h of xi not equal to yi. Okay, this is a loss that we would want to minimize. Now, what happens? We'll see. There is some problem with this loss that we have defined. So this actually, like if we are looking at this, just like the linear regression problem, here also we are looking for a linear classifier. Okay, so since we are looking for the linear classifier, what is my goal here? Now my goal would be to minimize this loss. Okay, so I want to minimize this loss. So let's call it L. We want to minimize this L, and where H should be my H linear. Okay, but how do you define this H linear in case of this linear classifier? So my H linear would be set of all the, a set of all the classifiers HW such that it takes the value as sign of W transpose X. So remember, like there, it was more like you're looking at W transpose X, but now here we want to see what is the sign of W transpose X here. And that is how we are defining this H of W as.
Ma'am, what is linear classifier, if you can answer?
Yeah, so let's say if you have a binary classification problem. Right?
Mm.
So let's say I have some data set here, and let's say I have another data set which is of different class on this side. Okay, so I want to come up with a classifier, and I'm saying linear classifier because we're looking at the linear, linear boundary. So we want to come up with such a classifier which distinguishes or which separates my one class from another class. Okay, so this is the linear classifier that we have it over here. So this is my positive class, and this is my negative class. So basically, classifier also is a function. It's a function uh, which uh, which separates your positives or one class to another class, in a sense.
Got it,
Okay.
ma'am.
Okay. So all right. So what I was saying is, this is our goal. We want to minimize this loss. Okay. So if I have to, like, let's say this is my W, and I'm saying everything on this side, it's predicting to be positive. So let's say this is set of all X such that my W transpose X is positive, and this is the set of all data point such that my W transpose X is less than equal to 0. Right. So, okay. Everything on this side, I'm going to predict it as positive, and everything on the other side, we're going to predict as negative. So, if you look at this loss now, this loss, so this is a discrete value, correct? It's not like our squared error where we were saying we will do h of xi minus of yi whole square. It's not like this squared error. Now this is a discrete. At every point, like for in this example, we saw that for every data point we have either 0 or 1, 0 or 1, 0 or 1, right? So this is some discrete value. So that makes this loss function non-differentiable. Okay, so and because it is not differentiable, it's difficult to come up with a classifier, come up with a model which will which can exactly give you the loss to be which can tell you like what exactly um, should your model be, right? So we can't solve this problem. Okay, so like as we were able to do it in the case of regression, where we were able to find out that W and come up with the model. But now in this case, we because of this non-differentiable nature or discrete nature of this loss, we are under this problem of like not being able to differentiate this loss function. So that makes it difficult. So now if we are not able to solve for this loss, then there should be some alternative way which we can which we should have so that we can come up with a classifier. In case if we have binary classification problem, we should have some different kind of techniques to deal with this problem of non-differentiability.
Ma'am, can I ask something?
Yes, tell me.
Ma'am, why we are differentiating? Or why we need function which can be
See,
differentiable?
we want to minimize this loss, right?
Yeah.
So what is the technique that you know which will help
Oh,
you?
yeah, got it.
Yeah, gradient descent
Yeah.
has to be zero
Yeah,
for the
got
minimum
it.
loss.
Right?
Yeah.
Ma'am, I have a question here. So
Yes.
here it is a linear classification, means the line separating the two region is a line. So can it be anything rather than line, any
Mhm.
polynomial or anything else?
It can be. It can be. But throughout this course, we are going to mostly look at binary classification problem and the linear classifier. But you will have non-linear classifier as well. Okay.
Thank you, ma'am.
Yeah. So now what do we need? We need some other method or some alternative way to deal with this problem of non-differentiability. So one way to see was, when we were using uh, the loss that we use for regression problem, can we use that loss to solve this problem is what we need to see, right? So like what happens is like if we use the regression method to solve classification to solve this classification problem, then in that case like there will be some data point for which your loss is 0, but due to the quadratic nature of your loss, right, this convex nature of your loss in regression, so it looked like this, right? It looked like a parabola. It will look like a parabola. Now, because of this nature of the loss, like even though this classification loss, which looks like this, and for some data point you will have 0 loss, but it is quite possible that you are going to get a very high loss for certain point if you use this regression loss for solving the classification problem. So this is not very ideal for us. I mean, what we're seeing is like there are data points for which the losses are for which you are getting the loss to be 0. But if I use this regression, this regression loss, which is squared loss, then in that case, for those values, it can be quite large. Okay, so let's say if this was the data point or this xi, now in this case the loss is quite big, but let's say if this was actually 0, so it doesn't make sense for us, right? So this is not a very good way to.
So, ma'am, if I can summarize, for regression, the loss is like it's a convex function, so it can be differentiable. But in this case, as there are only two y values, 0 and 1, so it become discontinuous. That's why we are not able to do this. Am I correct?
Yeah. That's why we are not able to differentiate this.
Ma'am, but it
Okay.
is differentiable other than 0. I mean, if we,
Yeah. At this point, it is not differentiable, right?
ma'am, it is not differentiable at 0, but it can be differentiable at other points in the
Oh yeah,
second figure.
correct. But that is what is making this loss to be like non-solvable, basically, right?
Uh,
So again, this comes under this NP hardness case, which we had seen again in the clustering problem, where we were trying to solve this objective function, where we wanted the distance between each of the data point to its center to be the minimum.
mhm.
But that was very difficult to solve. Again, here also, this is something which is very difficult to solve. Right?
Okay.
So that is what is causing the problem here. So now what we're trying to say is, can we like the way we had seen it in regression, where we had used a squared loss, can we use that loss and solve the binary classification problem? So it turns out that that isn't a good way to solve this classification problem. So for many point, for which for many regions for where the actual error should be 0, now this regression is giving me this square error is giving me a very high loss. So it is not really recommended. It is not really advisable to do this. So now, since it is not advisable, I mean, it is not very suitable for solving this kind of problem, then what we have is we have various different kind of like now from moving onwards, we will look at various different algorithms, so which can solve like not exactly it will solve this problem, I mean minimizing this loss, but whatever we are able, whatever model or whatever classification techniques we are going to come up with, it will kind of be very close to in solving this problem. Okay, so now we will look at those algorithms. So the algorithms that we're going to look at in this week of week 7, one is k nearest neighbor, which is the most simplest classification algorithm that one can come up with, and the second is my decision tree. Okay. So again, these are not the only models, not the only classification classifier. There are many more, and we will see how like not exactly in this week. We will see in week 11 like how all these algorithms that we have come up with for solving this binary classification problem, how is it actually solving this problem of minimizing this loss. But for now, we will stick to what exactly are these algorithms. So in this week, we'll look at k nearest neighbor algorithm and decision tree. All right. So let's start with k nearest neighbor first. So we have k nearest neighbors. What happens in the k nearest neighbor? So as the name say, k nearest neighbor, this is exactly what my algorithm does. So see, we have like we have if we are given a set of data points, and we want to let's say we have some maybe these points, and we have some other points with us in green color, some other class. The both were similar. Let me take some of the color. So these are my green points. Let's call it the positive points. And then I have some red points. Okay. This is how my data set is. Now, let's say I am given an X test. Suppose my X test is here. This is my X test. Let's call it X test. So if I'm given an X test, I want to know what is the label, what is the prediction for X test. Right? So this is what I want to know. So what we do in k nearest neighbor is let's say my k is given to be let's say 3. So I am going to look at 3 nearest neighbor to this X test. All right. So what are the 3 nearest neighbor that you can figure out? So one is this point, other is this point, and I think the other is this point. So these 3 points look the closest to my test data set. So for this these 3 data set that I have, one is this, and there is this, and there is this. So I am going to look at the majority vote, vote as in like majority labels maybe. So here I have 2 reds and 1 green, right? So what is the majority here? The majority is red color, right? And red was denoting a negative label, or let's say -1. Red was, let's say, -1, and green was, let's say, +1. Okay. So what should this algorithm predict for what label should my algorithm predict for this X test? It should predict the value to be uh, uh, red, right? Right. So
Yes, ma'am.
that's all it is. So if you have to write the algorithm, it's more like if you are given an X test, what you're going to do is you find, so we'll find the k closest neighbor to X test and take, and we can say predict Y test to be majority of this Y1 star, Y2 star, so on to star. Okay, that's all it says. But now here, see, this k is something that is you have to figure out. I mean, that is something you have to do, right? So like how do we see which k should be a good k? Okay, so my k is a hyperparameter again, like k is your hyperparameter, and this is something that we provide the model to. Okay, so what happens is like there is this we have we have to give a value of k to the model. Okay, so if what happens if k is equal to 1? So if k is equal to 1, I'm going to look at like the closest point to that data point, I mean to that axis. So it turns out that it is very sensitive to like outliers. Okay, so one in general, like what would you want k to be? Like if you just not a specific number is what I'm looking at. What I'm asking you is, if you are given this algorithm and you would want to um figure out what k should be ideal, like what should be your intuition in that case? What you would want your k to be? You would want your k to be such that it shouldn't, I mean, your loss that you get should be minimum. That is ideal thing, right? So we would want the k to be um, some value which can give us the loss to be as lesser as possible. Okay. And what is ideal k again for any specific problem? It's something that we cannot give theoretically, but for data set that we have, we'll have to perform the cross validation and come up with a k which satisfies, which suits your problem, right? So we'll perform the cross validation and come up with a value of k that solves the problem well. Um, but there are some drawbacks to this. I mean, even though it's a very simple algorithm, but there are some drawbacks to it, right?
Ma'am, how k is equal to 1 is sensitive to outliers? Can you explain, please?
Okay. I skipped that part. I thought it's in the lecture. All right. So, okay, let me give the example. Suppose I have a data set which looks like, let's say, these are all one group. Okay, I mean, let's say these are some one label, and there is maybe one point over here which is some other class, right? Then I can see there is another set of, I mean, the another label is mostly it's on, let's say, on this side, but maybe one or two is coming on the other side as well. So let's say these all are another label. But I see these two points which are on the wrong side, and here this point which is on the wrong side. But if you are given a data set and once you have visualized it, you see like majority of these positive class are in this side and majority of the negative class is on this side, then maybe this looks like a better classifier for us, right?
Yes, ma'am.
But what happens in this case is, let's say if I'm saying I'm using k is equal to 1. Okay. So if I use k is equal to 1, then every data point, let's take a set. Say this is my test data set. Okay. Now if I take k to be 1, then what happens? It will, since this test data set is on the positive side, it will predict the label to be positive +1. But what if this point is actually, the true label of this point is actually negative? But just because this point is falling on this category of positive side, I'm predicting it as positive, right? But actually it should have been negative.
And what if it is case 2 or 3? Number of points increases.
So as you increase the number of neighbors, so as you increase k, now, so if you increase k, so as k increases, now you are going to look at more and more neighbors, right? you are going to look at if you put 2, then again maybe these two are the closest, right? If you put k is equal to 3, then these two are closest. And if you put k to be more than maybe 10, then there will be some points coming from this side as well, right? So as you increase the value of k, you would expect this to perform well, right? But slower the k, not slower, smaller the k is, the more likely it is that that it might cause the problems here. Okay, but again, these are all theoretical. Just for this example, we can say, but if I have to actually find out what my k is, then for the data set, given data set that we have, we should perform the cross validation, and from there we should figure out what k best works for my data set. Okay, and that is the k we should assume that is the way that we should take for our algorithm. Okay, so your case should be somewhere balanced. Balanced as in, like, it shouldn't be like when you are taking this k, you are always making a wrong decision, isn't right? So you should have a k, an ideal k, which kind of balances out the regions that you have for the positives and the negatives. So somewhere you want to minimize the loss basically at the end. You would not want your model to predict more, uh, give more wrong values. Right? You want it to be giving more and more accurate values. So that is what would be ideal here, and that we can get only using the cross validation. Now, some drawbacks for this k nearest neighbor. What are the drawbacks? One drawback is that, see, we just said if we are given a data set, let's say if this was a data set, I am looking at the 3 nearest neighbor, let's say, right? So one thing is, like, we have to decide what is the distance function that we're using. Here we're using the Euclidean distance, but what if we're using some other distance? Okay? So one drawback is, like, we have to decide the distance function. This is one drawback. Then the second and the like, I would say the most, like, critical drawback is going to be, like, if your data set is small, you can still compute the distance of a data point through all the data point, and then you can look at the 3 closest neighbor. Still okay. But if this data set is large, let's say the data set is in 1,000, 5,000, 10,000, then computing the distance of a test data set to each and every data point is not really good, right? So this is going to take a lot of time, and we are going to repeat this whole process again and again for every data set, which is not very efficient for us. It takes a lot of computation. So it is not a good choice. Like, this algorithm is not really doing a good job, to say, because it's very computationally expensive as you keep on increasing the data set. And also, this is not something, so I will write here, so not computationally feasible, or maybe I can just write expensive. Right. So these are two problems. So, and also, like, there isn't anything that we are learning from this algorithm or this model. It is not giving us any model to say. It's just saying that any result you have, whatever k you get based on the cross validation you do, that k is something. You are going to like, keep looking for that number of neighbors every time you have a new data point. But that is not something you would want. You would want that if we are training my model, if we're training on my if you're training my model, I would want it to give something which I can use it later for any data set that we give. But here that is not happening. Here every time I have to look at those number of neighbors and figure out the prediction. So it is not really a very good algorithm, though it's a very simple algorithm, but uh, it's not very useful to say, right? So now let's see some another algorithm, which is decision tree. Decision tree, right? Okay. So the problem that we had, that it is not like this algorithm is not giving us something useful to be used later on, right? And decision tree is something that we'll see how is it helping to tackle that problem. And also, it is not going to be very computationally expensive as what we saw for KNN. So suppose like this was my data set xi ya, right? So we have xi ya, I is from 1 to n. This is my data set. Now, if I like if I give the data set to this function, I should be getting my output is going to be a decision tree. So the output that we get is basically a decision tree in this case. And how does the decision tree look like? So it's more like you ask certain set of questions.
Yes, no. Like
Yeah. So since so what we do is we ask certain questions. So maybe I asked a question here, and based on this question, I can split this into two parts. So if the answer to this question is yes, then maybe I can ask some other question, right? I can ask question number 2. If the answer to this question is no, I'm going to ask some another question. All right. If the answer, let's say, if the answer to question number 2 is yes, then again, let's say if yes, let's say I am predicting it as 1. If it's no, let's say I'm predicting it as 0. And again, if the answer to maybe question number 3 is yes, maybe I can ask some other question here, and then again based on that, if it is yes, I can predict it as 1. If it is no, I can predict it as 0, right? And if it is no, I can say maybe predict as 0. Okay, something like that is what we have. Now this is a decision tree. It means whatever problem you have, I am going to. So this is something called a parent node. Okay, like before we move forward, so this is something called as parent node, and all of these internal questions that you're asking, question number 2, question number 3, question number 4, all these internal questions are called internal nodes. Okay, and at the last, what you get, so the one that you're seeing in the boxes, prediction, is 1 0 1 0 0. So they are called whatever you get at the end, they are called leaf node or prediction. Okay, so these are the terminologies. Now, let's say I had a data set, and based on that data set, I got the output as decision tree. Okay, if the output is decision tree, let's say now this is my model. So now this is my model. So if I am given this model, and if I have to predict what label would this X test have, then what I'm going to do. So I'm going to put this X test into this decision tree that we have and see whether it, and just traverse through all the nodes that you have, like ask all the possible questions that you can based on this decision tree, and whatever prediction you get, we will come to that answer. So now from here, I can actually, like, I had a data set which was um, x1, x2, x1, y1, x2, y2, so on till xn, yn, let's say. And now based on that data set, I have come up with this model, I've come up with this decision tree. And now I can just use this decision tree to make the prediction for any new test data set that we have. Okay. So this is how the decision tree works. So I will just, if we have the decision tree, we can just walk through this whole tree and we can come up with the conclusion. So for this X test, what should be my Y test be? The Y test would be whatever value that you have in your prediction or the leaf node. So Y test is basically a value in the leaf node. So it's more like if I am walking through the tree, maybe I go there, maybe it comes out to be yes, and then it takes me to here. Then I will predict Y to be 1. But maybe let's say it was the color. Maybe X test was, maybe it was going through this network. It goes here, then it goes there, then I predict it as 0. Right. So something like this is how a decision tree will work. Now, what we are seeing is, once we have the decision tree, how can we make the prediction? So the problem of like coming up with something useful, which this decision tree is doing, like once we have this decision tree, we can just forget about our entire data set, and now we can just take this decision tree to make the prediction. But the thing is, like, we made this decision tree, but what are the processes involved in coming up with this decision tree, right? So, like, the very first thing that we're putting, I mean, we have to ask a question. Okay, so we have to ask a question. Okay. So the very first thing is, like, how do you determine which question is good, and what is what is that metric that gives you a sense of, like, okay, this is a good question to ask, right? So there should be some quantification for the question that you're asking. Okay, based on that, which we can decide, okay, the question that we have asked is a good question to ask, and once we ask this question, it is going to give a good decision tree, is something what we want. Now, so how do we ask this question? Like, how do we decide which question is good? So if we see, so basically these questions that we're asking, so these questions, it's basically a feature value pair. Okay, it's feature value pair. So what are the features, first of all? So if I have my data set, which are xi, yi, right? This is what we have taken. And I'm saying I is varying from 1 to n. Now, each of these xi we had said is in RD. And each of these yi's we said is in 0 to 1, 0 or 1. Okay. Now, if each of these xi's is in RD, then I will have my xi. So I will have this xi, which looks like xi1, xi2, so on till xid. Okay. This is how my this vector will look like. So, for example, if you just take, let's say, length, breadth, height. Okay, let's say if my xi has 3 features, it's in R3, and we have these features defined as height, width, and length. Okay, so these feature value pair basically should take some feature which should be either height, weight, or length, and some value associated with it. Okay, so maybe the first question that we thought to check whether the length is greater than 150 centimeter. I mean, there are many questions possible based on what data set you have, like what your data set has, how many features, how many values. I mean, there are various questions that are possible to ask. So, but whatever feature, whatever question you choose, you have to kind of come up with a metric that determines that this is a good question to ask. Okay, so like how do you decide that this question is good? So in general, I can say this is my feature fk and this is my value. Let's say this is the question that we have asked in the my parent node. So I'm asking whether fk is less than equal to theta. So it can give me two answers, right? If it does, let's say if my fk is basically denoting length, and if my theta, let's say, denotes some 150 centimeter for this example. Okay, so and if I am given a x test, which is so my x looks like height, width, and length. Right? So suppose this is 120, 180, 160. So if I'm passing this x test to this question, what whether it should come as yes or no? Fk is length, okay? Is it length is it equal to less than 150? No, right? So it will go there. Right? Now again, I will ask a question. Then again, in here I will have some question. Maybe fj is greater than equal to some theta 2 or theta 1 or maybe some other value we can think of. Let's call theta 1. So again, based on that, I will have some predictions here. Yes, no, based on that, I'll have some questions. So there is this term which is called information gain. And what information gains does is, so information gain. So this basically tells you how good the question is. Tells us the goodness of the question, okay? So what do you think should be a good question? Like intuitively, what do you think should determine a question is good? Any guesses? If I'm asking a question, if I have come up with a question, how do I say that this question is good?
Maximum likelihood.
Maximum likelihood. Why maximum likelihood?
Ma'am, like if we take the maximum likelihood, then it will be easier so that we can check whether the question is good or not.
Okay, so okay, I'll tell you.
Highest information gain.
I mean that's so we want highest information gain, but I have not told you about yet what information gain is. Yes, it gives you a measure of how good the question is. But in general, like if some question you're asking at the pairing node or at any node, and this question is kind of splitting your data set into two parts, yes, no, right? So you would want that everything that came to the yes part or everything that comes to the no part, right? They are actually pure, right? You would want the purity. I mean, when I say purity, it means all the labels here and all the labels here, all the labels here are same and all the labels here are same, right? So the features or the data set with the similar label should come on one side, and the data set with some another label should come on the other side. Then only we can say that the question that I have asked is a good question, right? So to measure that impurity, but that will always not happen. That any question you ask is giving you the zero impurity, right? So how do you check the sense of impurity in your data set?
Uh, so, ma'am, you mean we want it to be right skewed?
We wanted it to be right skewed. Is that what you saying?
We want all the questions to be yes
Okay,
to
yeah,
the
yeah.
left side.
Hmm.
Okay.
But yeah, so that is the ideal condition. But we may not have a situation like that where you ask a question and everything falls at the right place, right? So there is something called entropy. And what does entropy do is it gives you, it measures the impurity. Like it gives you a sense of the impurity. So measure of impurity. Okay. So like you would have heard this term entropy earlier also. Like it's more like randomness in the data set. And when we say randomness in the data set, it means the data set that you have, you would want it to be more homogeneous. Like you want the labels of similar kind to fall at one place and the labels of another kind should fall to another place. So you want to minimize that entropy. You want to minimize this randomness. Okay. So if let's say P denotes a fraction of data point with label 1. Okay. So if I'm saying in my data set, which is from x1, y1, so on till xn, yn, and my yi is basically belongs to 0, 1, since I have two labels, 0 and 1. And if I'm defining p to be fraction of data points, that is label 1. And if I have to draw this graph of entropy, so p is basically the fraction of data points with label 1, and this fraction will always be written 0 to 1. Okay. And if I have to plot the entropy with respect to p, then what we have seen it like one function. So what is ideal? I mean, what do we want? We would want that if fraction of data point with label 1 is 0, right? So if p is 0, okay, it means when we're saying p is 0, meaning what? So there are no data point with label 1 basically, right?
One.
So all the data point has label 0. So in that case, we would want the entropy to be 0. And again, if all the data point are of the same class, we would want again the entropy to be 0. The randomness will be 0 because all the data point are of the same label. So at the point 0 and at the point 1, we want the entropy to be 0. So one function that actually kind of and where would you want this entropy to be higher? Somewhere in between, we would want a graph like this basically. You know? So we want something which gives me the entropy to be lowest at p is equal to 0 and 1 and highest at or maybe somewhere in between. Because if 50% of my data set is of one kind and another 50% is of another kind, then the randomness is the highest. Okay, so at half, when my data set is equally split into two parts, we want the entropy to be the highest because the randomness is going to be high at that point, at that fraction, and at 0 and 1 it is 0. So one function that actually does this, so we'll define it. So we can define the entropy of P to be equal to minus P log P minus 1 minus P log 1 minus P. So this function actually looks like it has the shape of downward parabola, and it has the highest value at 1 by 2 and the lowest, and the value to be 0 at the point 0 and 1. So this function that we have defined here, it's called the entropy, and it gives you the measure of impurity in your data set, or a sense of randomness, which is basically to see how good, how pure the labels are, right? So entropy gives us a sense of impurity in the data set. All right. So this was about entropy. Now, to check how good the question is, so the question that we ask in each and every node, so that is given by the information gain. Okay, so information gain, like what it does is, so information, I'll call it as IG. Okay, so information gain, it basically checks what is the entropy of your data set. So entropy of D, let's, if my data set is D, what is the entropy of the data set, and you subtract like the proportion of like for example, if I ask this question, let's say this is not fair. Okay, we ask this question, and all the data set which falls into the yes category, I can call the data set as DS, and all the data set which falls in the no category, I can call this as D no, right? So now this DS will have a set of some data point, and this D no will have a set of some data points, and together they are basically considering the whole data set. So once we ask this question whether Fk is less than equal to theta, it splits into two parts, and there will be some data point which will fall into the category of DS, and there will be some data point which will fall into the category of D1. So now we will check what is the entropy of this DS and what is the entropy of this D1. So we have asked this question whether Fk is less than equal to theta, and we are trying to find out the information gain that we had by asking this question, and it is given by entropy of D minus the proportion of data point where you had like in DS, what is the proportion, like how many data set went to the DS side and how many data set went to the DNO side. You just kind of take the average or weighted average, you can say, right? So entropy of D minus the proportion that went to the DS side times the entropy of DS. And when you say entropy of DS, it gives you the sense of impurity in the data set which falls into the yes category, plus what proportion of data set falls into the no category times the entropy of D no. Okay, so like from if we measure the impurity from the whole data set, and if we subtract the entropy from these individual DS and the category or DNO category, then that kind of gives us a sense of how good the questions are. So when we are saying information gain, what do we want? What we would want is the more the information gain is, the better the question is, right? So more the information gain is, the better the question is, right? Because if the information gain is more, what we are saying is by asking this question, I'm able to remove more randomness, right? Because you are subtracting this part from the overall randomness. So if you're able to subtract, if this is quite, if this is high, then um, sorry, if only if this is low, you are getting this value to be more, right? So this kind of gives you a sense of how much randomness are you able to remove from your data set. The higher this value is, the better the question is. So we are looking for the question with the highest information gain. So let's say if I am given a set of questions, let's say I have question 1, question 2, question 3, question 4, question 5. Let's say 5 questions we have with us, and we have to decide which question goes to in the parent node. So I will have to compute the information gain for each of these questions, and then whichever question has the highest information gain will go to my parent node, right? Then again, it will proceed, you will proceed. And since this question you've already asked, now you will ask, like, again, you will check for, uh, once you have asked this question, and now if you the turn is to ask this question, what what question will have the lowest information gain is what we will check. So the same process we keep on repeating unless we reach to a conclusion, not a conclusion, unless the pure has become like the node has become pure, right? We would want that, but if we try to like bring it to such a such a place where the nodes have become fully pure, then that is more like overfitting my tree, right? For that you'll have to perform a lot of steps, and it's like you have completely fit your tree to make the training error to be zero. So again, that is also not a very ideal thing to do. So what we can do is again, we have to somehow stop at some place, and we have to in okay, like just as in KNN, where K was my hyperparameter, here also we'll have to this depth, like how depth, how like what should be the depth of my decision tree. So depth of DT is basically a hyperparameter for us. So again, we will learn this using the cross validation technique, and whatever depth you get for the decision tree, we will try to fit to that depth, and that should be good enough. Okay, so that was about the decision tree. Any question here?
Ma'am, how do we pick the height of the tree actually?
Height, not height of. I mean, we told the depth of the tree, right? You mean how many
So yeah,
depth we want to go? So that is again, depth of a tree is hyperparameter. Okay. So when you say hyperparameter, it's something that you have to feed to the wire in the model, and you have to figure out what depth is giving you the least error. Right. So it's a hyperparameter, and that's why you have to perform the cross validation technique to come up with an ideal depth, and that depth we will use to fit my tree.
okay.
Okay. But that
Ma'am,
you have to perform this. You have to calculate the information gain to figure out how good the questions are. Yes, tell me.
a depth in terms of the nodes or like the levels?
Depth. Okay, so when let's see. So let's say this is the parent node. So yes, no. So what is the depth of this tree?
Okay.
The depth will be one, right? Because you just asked one question. So it's more like it's called a decision stump basically. So whenever you're asking just one or two questions, one question, we call it decision stump. Now let's say if it's not like that, let's say I ask another question here. This is question one, this is question two, this is question three. Again, based on that, I have come up with something. Right? So here the depth of the tray is going to be 2.
Okay.
Excuse me.
Ma'am, in the PDSI course, no, like depth was defined by the nodes, but
Your voice is not very clear. Tell me again. It is defined as.
am I audible clearly?
You're audible now. Tell me.
Okay. So in the PDSI course, no, depth or the height was defined by the number of nodes in the levels.
Number of nodes. So
Nodes. That means like for a single
Branches,
node,
I think.
yeah, yeah,
can't
branches.
be because if you look at this now, if you have 1, 2, 3, 4, 5, 6 nodes, I will say you have 6 nodes for
No,
tree.
no, I mean like not number of nodes. It's number of levels.
Number of branch.
Yeah, levels of branches. Yeah.
So how are you defining the branches then? I mean, what would you say other than of the tree is?
Like supposing
No,
it
like let's say this is the tree, whatever I'm presenting right now. How many branches does it have? I want to know.
branches. Let's see.
Ma'am, like a Q1 to Q2 one branch, then Q2 to any yes or no, that will be considered one branch. This type.
So again, this is depth 2, right? If that is how the branches are defined there, that is depth 2. Even branches you're saying it should be 2.
Yeah. Okay.
Yeah. But again, that is something is hyperparameter. So we have to see for our data set. Yes, Kaushik, tell me. You have anything?
Ma'am, like in this internal node is 2 and leaf node is 4.
Yeah, so we have two internal node, one parent node, and four.
Okay. Okay. Got it. Thank you.
Any other question anyone has? Okay. So yeah, so that was all we had in like the KNN and decision tree. So these two are a very like just the most basic algorithm and classification. Um, Once we move forward to the coming weeks, we will see more complex models there. Nobody has any doubt? Anything?
Ma'am, like in question paper, it will be asked regarding internal node and all that for decision tree or something else.
In question paper, again, like we can't say that, no? You should be familiar with whatever has been taught or whatever has been asked in the assignments. So it depends.
Ma'am, we will calculate probability for entropy or probability will be given.
No, so that will again depend, no? So how many data set, like how does your data set look like? How many okay, so let's see. If my data set, the labels looks like this, say 1 0 1 1 0 0. What is my P? Can you tell me what is the P?
4/7.
4/7.
4/7. So what is going to be my entropy? Entropy of P. What is the entropy of my data set? So the way we have defined entropy, it is minus P log P minus 1 minus P log 1 minus P. So this will give me is it this, no? So once we know P, we can compute the entropy because that is the formula for entropy. So maybe you are given the P, maybe you're not given the P. Maybe you're just given the data set and from there you have to figure out what your P is. And maybe in some cases, if your question is maybe theoretical or let's say some context based, maybe it's hidden in somewhere the value of P and you have to figure out what your P is and then compute the entropy. Right? Similarly, like what should your gamma be? Let's say if this is how my labels look like, and on one side you asked a question. Let's say three data set fell here and set 4 data set fell here. Then what is my gamma? Gamma is 3/7, right? Right? Gamma was what proportion of data point fell to the DS side, what proportion of data set fell to the Dino side was 1 minus gamma. So proportion of data point that fell towards the yes side is 3/7, and 1 minus gamma would be 4/7. I think this will be more clear if you solve some problems. Have you tried doing any problem in assignment, maybe activity or practice somewhere? Okay. Oh, all right. Anyone else has any question? Yes, Kiran.
Ma'am, can I ask a question from week 5?
Yeah, sure.
Like when we are optimizing the adder function, no, like it was difficult to differentiate this x transpose w minus y got transposed into x transpose w minus y. But in the PDF, no, in the PDF made by Piyush, he has taken the whole square.
Yeah,
You said how he did.
yeah.
You will confirm with him. You said no.
Right, right, right. Yeah.
Uh, like I had some confusion. How is that possible?
Uh, yeah, okay.
We use a minus b whole square for real numbers. No.
Yeah, yeah. No, it's not square, as I mentioned last class as well. It should be transpose, like norm of x square should be x transpose x, basically. Um, okay, let me do it.
Ma'am, are you looking for the PDF?
Yeah, I'm looking for the PDF. Wait,
Can I share the link?
you show me the link. Yeah,
Yeah,
sure.
I can create that. It will
Yeah,
generate a link that is publicly.
but we had done the proof, no? Like when we were discussing week 5.
Proof? No.
Yeah, we had done the proof for this. I mean, not like not in very detail, but we had given the proof.
But I don't know how we get this gradient thing.
Okay, see. Okay. See, what did we have? We had my effects, FW, to be norm of X transpose W minus Y. This is what we have taken, right? Okay.
Yeah. Yeah.
So what can we write this as? We can write this as X transpose W minus Y transpose X transpose W minus Y. Right?
Yeah.
So this is nothing but W transpose X minus Y transpose. Okay. X transpose W minus Y. Right? So this is W transpose X transpose W minus Y transpose X transpose W minus Y transpose Y. Right? So, oh, sorry, I missed one term. So W transpose X, X transpose W, W, Y transpose X transpose W.
YW transpose X.
Plus Y transpose W transpose X, Y minus.
And ma'am, it should be plus of y transpose y. No?
This is okay. This is this. This is this. This is this. Okay. So this turns out to be X transpose W, right? And these two terms we are seeing they are equivalent. So I can just do 2 times Y transpose X transpose W. I'm not going to repeat why they are same because we have already seen it. This is what we have. Now this is if this is my FW, what do we want? We want to do the derivative of like we want this, right? Gradient of FW. This is basically doing rho F by rho W, right? So if you take the derivative, this term goes off, right? And these are the two terms that we are left with. Okay. So if I okay, the way we can like if you don't want to look at the complete proof, I mean just the like see this W transpose XX transpose W. This is a matrix for me, right? We can call it A. This is more like differentiating W transpose AW. I'm differentiating it with respect to W, right? So W transpose W is more like square for us now because WW is coming, right? So if the
Yeah.
when you do the derivation, it will turn out to be 2 times XX transpose W when you perform the differentiation. This is what you will get. Now, if you look at the other part, which is 2 times Y transpose X transpose W, it is just 2 times y transpose x transpose, because you're integrating with respect to w. Now we equate it to 0 and we just solve for it. Right? But again, like how is this? How are we able to do these differentiation? So see, what is like if you have to do the derivative, like what is the first thing that you have learned um, to do the derivative? So let's say if I have a function which is maybe f of x to be x square, and if I will take its derivative, I know it's very simple function. I can say it is 2x. But what is the definition here? So what do? We do limit of f of x plus h minus f of h divided by h. Right? This is how we do where h tend to 0. So we'll solve for this and we should be able to. So we do x plus h whole square minus x square divided by h, and we get, so what do we get? X square plus x square plus 2xh minus x square. This cancelled out. You have h in the denominator, then goes off. So you have 2x plus h basically, and limit h tend to 0. And what do you get? 2x. Right? So this is the definition that you follow to do the derivative. Now you are no longer dealing with derivative. Now you have vectors and matrices and so on. So in general, if you have to look for the derivative definition, right? So what we are saying is now your f is from some Rn to some Rm, and what we would want is, yes, Divyanshu.
Ma'am, will you cover a generative model today?
No, today is for week 7. That I have already done. So if nobody has any doubt from week 7, you can leave. I'm just doing the some parts from week 5, which Karan has asked.
Sir has covered in last lecture a little bit.
Oh, is it? But
Yeah,
I think we can do it in the next class.
7.5.
Yeah, yeah, okay. Okay. I've done it in this week. But we can do it in the week 5 because, oh, sorry, week 8. Because it's a continuation of week 8.
Okay.
Ma'am, what you're doing?
Sorry.
We got the gradient. No, what you're doing?
No, we got the grade. We got this and we substituted to 0 and we can solve for it. But I thought you had doubt on like why is it this? No, you didn't have the doubt.
Yeah, like we are taking norm squared of w. No?
Uh, yeah.
So
So
after derivating, it becomes like 2 into w.
right. But um, but vector calculus, I don't think I will be able to like to properly understand why is it why is XX transpose here and not Y outside, right? Or why is it W outside? Why is it not 2W? Then there are many things that you can have you could have asked here. Right?
But no, it is associative, no matrix multiplication. Also.
Yeah, okay, that is also fine. So but what I was saying is like the idea is that the way we are that we have started derivative, right? Whatever definition we have seen, the very first definition, the same you can build on the same definition, and you would be able to do the, I mean, derive this actually, like using this derivative definition as well. Okay. I hope till here it's okay.
Okay, ma'am. Like I was like wondering how it is a norm squared of W, no? How you can take that to into W.
Mm,
But then we are actually doing partial derivatives. No? We'll
yes,
be getting
yes.
such
In the
like
derivative.
yeah, that is like uh, norm squared of W is like W1 square plus W2 square
Mm-hmm.
plus and so on WD square. And after
Right,
taking
right.
the derivative, we'll be getting two common out, and then
Hmm.
um, we'll be left with W. Okay, thank you, ma'am.
Yeah. Okay, so that was all in week 7. Next week we'll be doing week 8. So once we start week 8, we will look at both the generative and distributive model. So in week 7, that has been introduced, yes, but it has not been covered in detail. It's more like continuation for week 8. So we'll do it there. Okay. All right then. We'll close the session for today. If there isn't anything else.
Okay, thank you.
Okay. Thank you, everyone.
Thank you.
Thank you.